Ta-da! Right, okay, so we're going to crack on now. Have you noticed? I don't know if you can see on the screen. We're on page 5. Don't worry, we've got 19 pages to get through in full. We're going to do that in the next hour. Awesome. Okay, so string. Can you just about see that? Is anyone on a phone? Just to double check, can you see the whole page? Yeah, obviously not. There's no writing on it, but can you see the sort of whole page? No. Megan, you're on the phone. So do I need to zoom out a bit? I think that's what she's telling me. Okay. Better? Same? Worse? Bit more? Talk to me, Megan. Bit more would do it. Okay. Fantastic. Probably didn't need to record that bit. Never mind. Anyway, let's crack on. So good. Fabulous. Great. Oh, awesome. Okay, so it just helps a little bit, doesn't it? So what we're doing now, so I'm going to make my, it's a little bit small for my screen. I'm going to pin it. Where are we? Pin. There you go, pin. Oh, I can see a bit better now. Good. All right, so lovely. So strings. Okay, so the next bit is sort of to do with strings, but it's also generally as well. But we're going to have a look at strings. So we're going to use 2 terms. One is the fundamental frequency. We're going to find out what that is. And we're going to find out what we mean by a harmonic. Fundamental frequency, harmonic. I've not seen them ask you to define that. You know, state what we mean by the fundamental frequency, state what we mean by a harmonic. But I'm just going to move the background. Here we go. I think because we're going to use those words, it's nice to have a clear understanding of what the heck that word means. All right, so this is the first one. So the fundamental frequency. So this is the lowest frequency. Low frequency. I can't do low. Low. No, it's not going to work. So lowest frequency in a harmonic series where we create a standing wave, where a standing wave is produced. Full stop. Okay. We give it the symbol F0. So F would just be any old frequency. And then F0 is the fundamental frequency. We may also call it the natural frequency of that string or that column of air, but we're really going to say fundamental. But you might, we're not going to do it, but you might see in some places when they talk about the natural frequency of a swing that we talked about earlier, they may use the symbol F0. Okay, and of course it's just frequency. We measure it in hertz, like anything. Yeah, so frequency of like the oscillation. It's the lowest frequency. That's the thing to maybe remember. Is it's the lowest frequency in a harmonic series. So what's a harmonic series? We're going to come to that. But this is this is like the first one. It's the lowest. Okay. So harmonics, what are they? Well, again, it's associated with a standing wave, and we're going to sort of see that applied. So we'll see this in a bit more in a minute. But it's a whole number multiple of the fundamental frequency. So we sometimes call it an integer multiple of the fundamental frequency. Okay. So and that's what we mean by harmonics. So let's see how they relate together a little bit. Pause. Let them take in the information, John. I'll try, John. Thanks, John. Okay, so whole number multiple. All right. So, oh, my mouse is in the way. So, oh, okay, that's fine. So, look, oh my goodness. Great. So, what are we looking at? So, F0 is the fundamental. So, imagine we had a string, certain length. Fundamental frequency might be 100 hertz. Let's say it's 100 hertz. We would call that, if its natural frequency was 100 hertz, then when we pluck that string, it will vibrate at 100 hertz, whatever that sounds like. And we would call that the fundamental frequency, and we also call it the same thing. It's the first harmonic, whole number multiple. So this is like the fundamental frequency times 1. Only we don't usually write the 1, because 1 times something is just something, isn't it? So fundamental frequency, the first harmonic of this series. Okay, same string. We now sort of increase the frequency that the string vibrates. The standing wave will die away until we get to 2 times the fundamental frequency. Okay, 2 times the fundamental frequency. Well, that's a whole number multiple of the fundamental. And so this is the second harmonic. So we get a standing wave created. All right, and the string starts to vibrate. And we'll look at the shape of the thing in a minute. All right, so that's the second harmonic. Third harmonic, it's 3 times. So 100 hertz, for example, if that was 100 hertz, then as we get to 110, 120, 130, 140, everything dies away. Nothing happens. No sound. pretty much. And until we start to get to 190 and then 200 hertz. Ta-da! 200 hertz is 2 times the fundamental. We get a second harmonic. We get a standing wave created again. Okay. We keep increasing the frequency. And then what happens? Oh, basically it all dies away again, doesn't it? So 100 hertz, 200 hertz. So I don't know, 210, 220, 230, 240, 50, and then 270, 280, 290, and then 300. 3 times the fundamental frequency. We start to get a stationary wave again, and that we call the third harmonic. Sorry, third harmonic, and that carries on. I feel like I'm a little bit of an angle. Hang on, let me just change things a little bit. Okay, so. Okay, it's better, I think. All right, and so that would carry on. We'd have a fourth harmonic, 4 times the fundamental frequency. Fifth harmonic would be 5 times the fundamental frequency, 500 hertz in our little example that we're talking about. That's fine. And this pattern is the true whether it's a string or an open-ended tube. Okay, string or open-ended tube. We're going to look at open-ended tubes as well. Okay, hope that's reasonable. Any questions on that so far? Talk to me, people. Right, I'm going to pause. Just let you soak it in. No questions. That's fine. All right. Cool. Lovely. What's next? Okay. So next thing, let's have a look at how it looks. What it looks like on a string. To be honest, I might just do one bit at a time. So let me just try and cover up a bit. Oh, it's all blurred anyway. Mm-hmm. Come on, you know you want to. Wake up. Okay, there you go. Nice one. Oh, maybe I'll just do that. Small steps. Lovely. Okay, so here we go. Here's our guitar string, maybe, or a violin string. We've plucked it in the middle or drawn our bow across it and caused it to vibrate. It's vibrating at its natural frequency, which we will call the fundamental frequency. Look, nodes. Look, antinode. Antinodes. And that's what a full wave would look like. So let's have a look then. So the length of this string, did I draw that? No, I didn't. That's okay. So if we look at the length of this string, okay, so this is a node, antinode, node. All right, can remember destructive interference, constructive interference in the middle. What's going on here then? So if that's what a full wave looks like, yeah, that's one wavelength. Obviously not the same size, but that's what it looks like. So what part of a wave? Oh, what? Okay. Do you mean because I've covered it up, Megan, or do you mean? Oh, okay. Have you got it pinned? So you can't see my hand waving then? That's weird. Oh, is it? Unless you pretend your phone horizontal, but you might have done that already. How does that work? It's filling the screen. Oh, okay, not yet. It's a surprise under there, so that's fine. Sorry, I'm with you now, Megan. That's great. All right, so we'll come and I'll do that in a minute. So lovely. Is what was the question? Oh yeah, the question is, before I tell you the answer, is, or you tell me, I want you to tell me, is what fraction or what part of a wave? How many waves is that? Or what fraction of a wave is just that bit? Do you think? What does it look like? Okay, cool, lovely, and that's what I'm trying to look for. Yeah. So the fundamental frequency for a string, it just vibrates about the middle bit, and so you might be able to see if I put my finger over that bit. Yeah. So I could do that, couldn't I? Really? Just adding to this a little bit, but then that bit looks a bit like that, and that bit is just half of a whole wave. So what that means is the length of the string, the guitar string, is half a wavelength. And that's what the first harmonic looks like. Okay, we're going to use that in a minute, but that's what I want you to associate. That's what it looks like. Fundamental frequency. The length of the string would equal half a wavelength, and so that's the first harmonic. All right, so yeah, we're not doing that yet. All right, let's have a look at the next one. Okay, so again, let's just, our hypothetical example, that could be of 100 hertz. That's vibrating at 100 times a second, 100 hertz, okay? What if we then force it to vibrate at not 100 hertz, but 200 hertz, okay? Ta-da! So that'll be our second harmonic, remember? 2 times the fundamental frequency. And we've got this shape, all right? So what we do is, as we're going up, you'll notice that I've got how many nodes? 1, 2. I've got 1, 2, 3 there. So I've added a node. I've got 1 antinode there. How many antinodes? Excuse me. 2 antinodes. Yep. So every time I go up, I'm adding an antinode and a node. First thing to look out for. Okay. So, and thanks for your contributions, by the way, other people, for the last question. So next thing then is, oh, what part of a wave is that then? What fraction of a wave is that? Can people in the chat tell us? And I don't mind if I get 15 answers, or 14. So people tell me, what of a wave is that? Okay, thanks, Abby. And anybody else? What do the other 13 people in the room think? Okay, so have a look at that and compare it to that. If that's a full wave, what's that? Okay, so we're going up, down, and then back up again. It may not be that easy to see, I don't know. But if you look at that, that's doing the same as that. And so this is now a full wave. What we've done is we've had half a wave, and then as we double the frequency, we've now got a whole wave. Hello. Cool. It's not focusing. Persevere, John. It's going to be worth it. Okay, well, thanks, John. Lovely. All right. So, yeah. So what we've done is we've added another antinode and a node. We've basically gone from half a wavelength to a whole wavelength. We've added half a wavelength kind of thing, but still with the same length of string. The string stays the same length, but it's now 2 times the fundamental frequency. And so 2 ways we can think of that is we're actually adding half a wavelength each time. And also what you can associate is, have a look, fundamental frequency 1, and that's first harmonic, and that's half a wavelength. Now we've got 2 times the fundamental frequency. We call that the second harmonic, and now this is 2 times that half a wavelength. We've doubled it. And obviously we know that 2 over 2 is 1, so that's just really, actually it's just 1 wavelength, so nice one. Okay, and this is a pattern that we get. So if you follow the pattern, you, yeah. This is his normal lesson. If you can make it, please, yeah. All right. Well, okay. Anyway, that's fine. So anyway, just Omar asking in the chat. So hopefully you'll join us soon. All right. So yeah, both bubbles. Everybody's online. Okay. Cool. Yeah, put a message in Google Classroom. Hopefully got it. Lovely. So yeah, so we've added a node, and we've also, let's have a look. We've actually got, some people remember it this way. I've got 1 antinode, 1 times the fundamental frequency, 1 lot of half, 1 harmonic. 2 antinodes, 2 times the frequency, 2 times a half, 2 second harmonic. Okay, guess what we're going to do now? So we're going to have a look at maybe just one more, because basically once you've got this, you've got it, haven't you? So guess what? If we increase the frequency a bit more, in our hypothetical thing, we went from 100 hertz to 200 hertz, now to maybe increase the frequency to 300 hertz, causing it to vibrate even faster. Again, we've got a load of nodes, we've got a load of antinodes. Notice now, oh look, we've got 3 antinodes. Can you see? I've got 2 halves. I've got 1 half, 2 halves. How many halves? Someone tell us. Are we alive?
1.5.
Yeah. Okay, that's not how many, that's fine. How many halves? So 1.5. Have we got 1.5 halves? No. You meant it's 1.5, isn't it? Yeah, 3 halves, which is the same as 1.5. Yeah, brilliant. All right, and it's a third harmonic. Okay, so quite right. It's 3 halves of a wavelength, 1.5 wavelengths. It's really what it is. A third harmonic. You see, 3, 3, 3, 3. All right, so we've got a little pattern happening there. Okay. One thing, last thing to point out, with a guitar string, we always have the ends fixed, don't we? So we always have a node at the end of a string, at both ends of a string. Yeah, can't have an antinode there, always have a node. Okay. Other things, depending on the frequency, can change, but oh, okay, that's fine. Lovely. Obviously, he's going to do his best. That's fine. Okay, so how can we use that idea to maybe solve a problem? What kind of questions? So whether you might get a question about labeling where the antinodes and the nodes are, you might get that. Maybe identifying that it's half a wavelength between two adjacent nodes, or possibly just using it. Or you might get a question like we're going to look at now. So maybe crack open your calculators. All right, so imagine you got a diagram like that, and you're told that the length of that string is 0.5 meter. Things that they might ask you are these things. How can you work out from that diagram, can you work out the wavelength? And if you've got a wave speed of 200 meters per second, could you work out the frequency? All right, so we'll have a look. Grab a calculator, see what you think. So we'll just do this together. And when you look at some of the practice questions, you'll see that this has come up before, and you can practice doing this yourself. So let's have a look. So okay, and then what would be the frequency of the second harmonic, etc. All right, so that's going to be fairly straightforward. So if that's 0.5 meter, can 15? Actually, should we all have a go? So what I'd like you to do, I want you to type your answer in the chat. How many meters is the wavelength? But don't press enter. Is that okay? And then we'll go 3, 2, 1, and all press enter at the same time. All right. So the question is, if that's 0.5 meter? Look at your previous notes. What would the wavelength be? Don't press enter. Type your answer in the chat. And then in a minute, we're going to go 3, 2, 1. 3, 2, 1, go. Right, I'm going to ask the question again because I think, hi Kia, and she just joined us, brilliant. She might be just logging in now. I'm going to ask the question again. What is the wavelength in meters? So people have identified that that's half a wavelength. Maybe that's what you were telling me. I think that's what people were telling me. But if that's 0.5 meter, what does that mean about the wavelength? So have a look at your previous notes. Tell me in meters. So don't type the answer. Thanks, Kia. I assume transport. Send me an email if it's otherwise. And so the question is, how many meters is the wavelength? This distance here is 0.5 meter. Oh, we're supposed to do 3, 2, 1, go. Go. Okay. So how long, so not how long that is, how long would a wavelength be if this fundamental frequency is 0.5 meter? Okay, 4 people have had a go. What do other people think? Okay, that's cool. Okay, let's have a look then. All right, keep typing your answers if you haven't already. There we are. Oh, good. All right, so before, what did we say? We said that the length of that thing for a fundamental frequency, that is half a wavelength, correct? People sort of said that. So that's the length. So if that's half a wavelength, my question is, how long is one wavelength? What do people think now? Kia, it might just be worth, if you just leave the Google Meet and then come back in again, just in case it's a camera thing. I don't know. Or it won't be a camera thing, it's my camera. We can see all right. Yeah, so worth a try, Kia, if you want to. Oh, she's done it already. So what do people think? More people. So if half a wavelength is 0.5 meter, what's one wavelength going to be? Type in the chat. What do you think? Can you see okay, Kia, by the way? Cool. Lovely. All right. And so the answer is, let's move that needs to be, great, is if the length is lambda over 2, then we can rearrange that equation to make lambda the subject. You could put it in a triangle, or you can just know that if that equals half a wavelength, one wavelength is just we double that side, and therefore we have to double that side. So one wavelength is 2 times the length for this particular waveform, and therefore 2 times a half is just 1. Yeah, so I can't remember who it was. I think it was Asher and somebody else said 1 meter at the start. So well done for those guys. A couple of people said it now. Does that make sense? So if it's oscillating at the fundamental frequency, vibrating at the fundamental frequency, then this is half a wavelength. So therefore, to work out what one wavelength is, we just double it. Cool. So give me a thumbs up or a thumbs down if that makes sense. Or say yes in the chat, yes or no in the chat. Yeah, that's all right. I'm not sure if my nod's working. Oh yeah, no, it's working. 50-50. Thanks, Fazan. That's great. All right, so let's have a look at that. So what we're saying is when we look at our patterns, so the first thing you'd need to do, have a look at the diagram, figure out what fraction or what multiple of a whole wave that would be. And in this case, you can see that that's that one. And that you've got to remember that that's the distance between two nodes is half a wavelength. So if 0.5 equals half a wavelength, then that means that if we double it to figure out what a wavelength equals, it'll be doubling that 2 times. Okay, we'll have a look at another one in a minute. Let's just go a little bit further with this one. So what's the next question? Oh, so next question is, if velocity is 200 meters per second, so the wave's traveling at 200 meters per second, what would the frequency be? All right, and so you might be aware in your formula sheet, you'll see that V equals F lambda. All right, so we're tying in that equation again that we looked at several, not too far after the start of the year, actually. Okay, you can do it in your calculator. You need to rearrange it. What do we think? Should we try again with our answer thing? So don't press enter. Are we all listening? Don't press enter. Type your answer in, what you think it might be. So remember, we're trying to work out the frequency. We know what the wavelength is now. We know what the wave speed is. So type your answer. Don't press enter, and then we'll go 3, 2, 1, and then we'll all go at the same time. Okay. We're all working on assignments or listening to music, or we're all right? We are actually listening. That's good. I hope so. All right. 3, 2, 1, go. Good. Wasn't everyone quite at the same time, was it? But that's okay. But maybe we're still working it out. That's all right. So let's have a look. It's quite an easy one to work out, of course, because we just got 1 in there. But mathematically, but let's have a look. So V equals F lambda. If you're not sure, put it into a triangle. So a little bit small on my diagram. But V would go at the top, F and lambda go side by side. We're trying to work out the frequency. Put my finger over the frequency. I've got V over lambda. So in this case, V is 200, and in this case, lambda was 1. So it's just 200 divided by 1, which of course, it's not particularly hard. It's just 200 hertz. No worries. Yeah, I'm not sure what Paris was doing, but thanks anyway. You had a go. What about the other 5 or 6 people that didn't even have a go? All right, so 200 hertz. So that's all you do for that. You work out the wavelength, which you've got to remember whether it's the fundamental 2 times the fundamental frequency, 3 times the fundamental frequency, etc. from the diagrams before. And the last little question was, what would it be if it was the second harmonic? Okay, well, now we know what the fundamental is. Hopefully it's not too hard. The fundamental is just 2 times, sorry, the second harmonic is just 2 times the fundamental. So it just ends up being 2 times 200 from our previous answer. All right, which is just 400 hertz. Okay, we're going to do another one. All right, let's see if you hear anybody on the second go. We're doing okay. We've got half an hour to go. Keep hanging in there. Hang in there, everybody. It's going dark outside. I feel sleepy already. Just going to play some slap bass on my face. Keep me awake. Okay, so. Yep. Oh, no, too fast. Okay. All right, so imagine they gave you this one. All right. So they'll give you this waveform. They're telling you that that is 60 centimeters. Okay. Little hint here, we need to turn that into meters, but we can do that in a little bit. And the first question is, oh no, that's all right. That's not the answer, thankfully. So the first question is, what's the wavelength? Okay, have a look at the diagram. Okay, well, I would do, John, but it's gone blurred again. Thanks. Man, it's not staying in focus at all. There we go. See if it'll focus on the pen. I think it focuses on what's on the center of the screen, and that diagram's not on the center of the screen. All right, so just about still awake. Good, lovely. All right, so what I want you to do again, let's try again. Let's type what you think the wavelength would be. Look at the diagram carefully. Have a think about which harmonic it might be, what fraction of a wavelength is that diagram or whatever, and then work out your wavelength. All right, I'm going to give you another sort of 10 or 20 seconds. Don't press enter, just type in your answer, and then we'll hit enter it in a minute all at once. We'll see what happens. So again, that's the question. What's the wavelength? This is your diagram. We're told that that length is 60 centimeters. Okay. Technically, I should have 14 answers about to come through. 3, 2, 1, go. Very interesting. Okay. All right. Thanks for your answer. Let's have a look then. So I don't even have to need to know what one person got it right. So I don't have to know. I don't even have to know whether it's a first, second, third, fourth harmonic. What I need to do is just look at the diagram and figure out how long is one wavelength. So remember, one wavelength is just sort of up, down, and back up again. So how many wavelengths can I see there? So no, I can't. I can see. So that is one wavelength. Can you see? It goes up, down, and up again. So no worries. Yeah. So it's in fact that is 1.5 wavelengths. Cool. I'm with you now. I think I can maybe understand a little bit where people are coming from. So that's 1.5. So how long is one wavelength? Just type in now. How long is one wavelength then? If that's 1.5 wavelengths, how long in centimeters is one wavelength? Yeah. All right, Amina. So what we're saying is, in this diagram, we can think of it two ways. It's either you can think of it as, well, one wave up, down, and back up again. That's one wavelength. That's what a wave looks like. That's 2/3 of this. So 2/3 times 60, bung it in your calculator, is 40. Okay, that's one way of thinking about it. You could also think about it. It's gone again. Where's my notes? Here we are. You can also think about it. Need to get a crack on now. You can also think about it. If my camera would just focus a little bit, please help me. Please. Oh, there you go. Focus. Focus. Okay. So not that diagram. This diagram. Right. Lovely. So can you see? So each one of those loopy things is half a wavelength. One loopy thing, half a wavelength. Two loopy things, two wavelengths. Two halves of a wavelength. In other words, one. This one has got 3 loopy things. So that's 3/2, 3 halves of a wavelength, which is the same as 1.5. Okay. Oh, I don't know. Is that okay? Is that okay? All right. So that is 1.5 of a wavelength. So you've got to look at the diagram carefully. These have been sort of typical. These have been questions before, not every year, but certainly some years. Okay. And so all I'm doing there is if how can I sort of show that a bit better? Let me show on a different bit of paper, maybe. Okay. Oh, this is so annoying. Here we go. Come on. Okay. Lovely. So what did we say? So for that, I've drawn that quite badly at the end there, haven't I? So if that's 60 centimeters, we're saying that that length is 3 halves, 3 times halves, yeah, of the wavelength. All right. If I rearrange that equation, how do I do that? Well, if I want to get lambda on its own, I'm divided by 2, so I'll do the opposite. I'll multiply both sides by 2. It will cancel on this side to get 3 lambda. So this is where we need to rearrange equations properly rather than just using triangles all the time. Okay, so listen carefully, look carefully, practice this. Yep, so it will cancel on this side. 2 over 2 is 1, so it just cancels, doesn't it? And then to work out lambda, I've got it multiplied by 3. What do? I'm going to divide by 3 on both sides, so that becomes 2 over 3. L equals the wavelength. 3 over 3 would cancel on this side. Yeah. So it's 2/3. In other words, that's fine. So 2/3 multiplied by 2/3 is equal to dividing by 3 over 2 or dividing by 1.5, which is what I did there. I divided by 1.5 there. So that's the same thing. So if we multiply 60 by 2 times 2 over 3, that's going to be 40 centimeters. Okay, that's where that 40's come from. That's the idea. Yeah, so there's a couple of people I knew were going to be late, so I've tried to record this a little bit. And we're also going to put notes on as well. So don't care, I know you came in late, so don't necessarily try and record everything down. It's good to try and get some idea of the diagrams and the relationships, but maybe it's more worth listening, absorbing, understanding, so you don't miss anything. Okay. Groovy. Okay. Oh, right, lovely. Okay, so next thing, we'll do the same thing. So that's the wavelength. So what would... Oh, okay. Okay. So next question would be, if we knew the wave speed, then what would the frequency of that wave be? Okay. All right, so this time... Oh, actually, I'll just explain it there. Oh, that's all right. Oh, I've just done it all. It's all over there. Oops, answers. Lovely. So the next thing, if we wanted to work out the frequency... Oh, my goodness. All right, so the next thing is, if I want to work out the frequency, if I'm told it was 200 meters per second, is that what it was before? Can't remember, I think it was. Then, so I'm just plucking it. This will be interesting, see what happens. Oh, it's a different length of string, so it won't be the same as last time. If that's 40 centimeters, before I put it into here, I've got to convert 40 centimeters into meters. And you may have seen that to do that, we just divide by 100. So you've got to remember that. Make sure you remember that when we're going to use it in this equation, it's got to be in meters. Okay. That's in meters. The wavelength has to be meters, can't be in centimeters. So, yeah, all we do is divide by 100, and that means that 40 turns into 0.4. Okay. And so, just for a little bit of time, I think we'll just talk through this one. So, like before, frequency would be velocity, and we divide both sides by the wavelength. So it's velocity divided by wavelength. This time, velocity is 200. The wavelength was 0.4. So if we get 200 divided by 0.4, shove it in your calculator, I think it comes out to be 500 hertz. All right, so if, obviously if you're making notes, jot that down, but you will get a copy of that. The process is the most important. Once you've worked out the wavelength and you've got the velocity, you're going to look for that equation in your formula sheet, convert your answer into meters from before, rearrange the equation, shove your numbers in, see what your calculator says, correct units. Okay, I'm going to pause. Is there any questions about that? Cool. Thanks, Nathan. Okay, let me know if there is. Right, next one. Now what we're going to do is we're going to go out of focus again. Okay. This time we're going to look at an open-ended tube. All right. Just stay calm, John. Just relax. It's going to be fine. Okay, here we go. Right, let's crack on. All right, so next one. Let's have a look at an open-ended tube. Okay, so this is our first situation. So this is a tube. So it's just a tube. Could be like a cardboard tube, toilet paper tube. Just blow down it. This is what you'll get. If you get a loud noise, you've set up a standing wave, a stationary wave in it. And this is what it would look like. So first thing, just to appreciate. Okay, so have a look. So what I've tried to just illustrate here is, oh, that's the thing. I'm not drawing these things very well. This is not a string that's oscillating now. This is air particles. Okay. Now, is air, when a sound wave, air, this is what this is that a longitudinal wave or a transverse wave? Someone tell us in the chat. Longitudinal or transverse? An air wave. Longitudinal or transverse? Anyone brave enough to have a go? Longitudinal, it is, all right? So this thing, this waveform we've been drawing, on a string you get a transverse wave. For tubes, you get a longitudinal wave. And what that means is, remember we had these compressions and rarefactions, they want you to know those terms, that the particles are just basically vibrating about a fixed position, but they vibrate along, parallel to the direction that the sound wave's moving in, if you like. Now, if we try to draw that on a wave diagram in a tube, everything's going to get bunched up and overlapped, and it's going to start to become quite crazy. So what we tend to do with these diagrams is we're going to represent, although we know it's a longitudinal wave and the particles are vibrating like that. So if there was no particle vibrating, that would be a node. If we get a large vibration, that would be an antinode. That's what it would look like. Okay, you can't see air particles, but that's what it would look like if we could color them in any way. All right. However, the diagrams get messy. And so what we tend to do is we tend to go back to our transverse wave representation. But I just want you to make a mental note that it is a longitudinal wave. It's not actually like this, but this helps us to see where we've got the antinodes, large vibrations, except it's actually there, large vibrations, and also where we've got the nodes. So that's a node, but basically the air particles aren't moving there. They're not moving there at all. No displacement. Remember, node, no displacement. A antinode is a maximum displacement. Okay, so let's have a look. If we have a look, this is what we have. And so with a string, if you'll notice, we're forced to have a node at each end. Node at each end for a string. Remember that. For a tube, an open-ended tube, then we're forced to have an antinode at each end. It's the opposite. Okay, because there's nothing stopping these particles moving backwards and forwards. Okay, we can't have an open-ended tube with no nodes in at all, so we do get a node in the first one. So let's have a look at that then. So first of all is, well, I've already sort of given you the clue there, but let's have a look. So this is the lowest frequency, so we call it the fundamental. Okay, this is the lowest note as you're blowing down your tube. That's what you'd hear. Lowest note, we call it the first harmonic. Okay, let's have a look at a wave. So if we look at that shape, I'm going to say what fraction of a wave is that? Well, I kind of told you there, haven't I? It's half. So let's have a look at that. There's my wave. If I actually just chop off that quarter and chop off that quarter, can you see the bit that's not covered up is a little bit like what's going on here? All right, and so if we've got a whole wave, take away one quarter, take away another quarter, then I'm left with 2 quarters, which is a half. And that's what we're representing there. So for a fundamental frequency, the first harmonic, the length of the tube, again, is half a wavelength. Okay, we're going to see a bit of a pattern similar to what we had before. All right, let's have a quick go through. All right, just for time, because I need to do a bit of optics with you as well. All right, so what happens? That's if, again, example, what if that was 100 hertz? Then I cause the air to vibrate at 100 hertz. I get a standing wave, large amplitude oscillations. I can hear that note quite clearly. As I crank up the volume, not the volume, if I crank up the frequency, the waves all die away until I get to 2 times the fundamental like we had before, the second harmonic. Okay? and I'll hear a standing wave again. But what would that look like? Well, we've got to have antinodes at each end. But like before, I've basically, did I write it in? No, I've not written it. There we go. I've bunged, like before, I've bunged in an antinode, I've bunged in a node. Okay, that's all, that's what we've added. Okay, so let's have a look at that. What does that wave look like? So it starts at the top, it goes down, and then it comes back up again to the top. So we're back up where we started. Okay, now it's not quite like that because it's basically, I've just taken this bit off, started at the top, and then I've brought that on and added it at the end so that I finish at the top again. But you may be able to see that the length of that is a whole wavelength. So the length is equal to one wavelength. What am I doing each time? I'm adding half a wavelength each time. 1/2, 2 halves, which equals 1. So let's have a look at that. Second harmonic, 2 times the fundamental frequency, 2 times half a wavelength. Okay. This time I'm not going to look at antinodes, but have you looked? I've got one node, 1 times the fundamental frequency, first harmonic. 2 antinodes, can you see those bits? No displacement. 2 antinodes, 2 times the fundamental, 2 second harmonic, 2 times that. All right, so there's a bit of a pattern there. Guess what we're going to get with the third one? All right, so the third one, and now increase it from 200 hertz if that was our fundamental frequency was 100 hertz. So 200 hertz, increase it, everything dies away, can't hear much to be honest. And then when it gets to 300 hertz, 3 times the fundamental frequency, I get a standing wave again. I start to hear a note, but of course it's a higher pitch as we keep going up. And then, you know, I might just, the pen's gone, might just add in, I've got 1 node there, I've got 1 node there, I've got 1 node there. 3 nodes, 3 times the fundamental, third harmonic, and now this length. The length of the tube hasn't changed, I've just increased the frequency, and we notice that now the length of the tube matches up with 3 halves of a wavelength. And we know that 3/2 is, well, it's 1.5, isn't it? 1.5 wavelengths. Okay, so hopefully you can see the pattern. Always having an antinode at the end, antinode, antinode, etc. Okay. So open-ended tube, the sequence and the pattern is very similar. Now, a few of you might have looked at something called a closed-end tube, where we block off the end. That's a bit more like a milk bottle. And the patterns are slightly different. But to be honest, I've never seen them ask about it. They don't really refer to it. So if you do come across it, great, but we're not going to bother too much. We've looked at a string, we've looked at an open-ended tube, and you can sort of see the pattern as we go from fundamental frequency, 2 times the fundal, 3 times the fundamental, and the relationship with what happens to the length of the tube. The length doesn't change, it's because the wavelength is now bunching up as we increase the frequency, and it's how much we can fit in. All right, so again, you'd then be able to do sort of calculations a bit like this one if you had an open-ended tube, where you'll know that for that shape of graph, that's half a wavelength, that's a whole wavelength, that one's 1.5 wavelengths. If you know the length, you'll be able to work out the wavelength. If you know the wavelength and then the speed, you can work out the frequency, that kind of thing. So just be aware of the kind of thing you're going. So go over these again. You're not going to get this all first time. Go over this again several times to make it clear. All right, going to look at the next thing. Okay, so we've got to press on a bit because we've only got a few minutes left. I want to get into optics. So I'm going to upload the sheets, but this next bit's going to be quick. So just try and listen, see where you get to it. If you look at the video again, you can always pause it and go back. So one of the things that we asked you to do on that, I asked you to do for that stationary wave exercise was look at this relationship between wave speed, tension, and this thing called mass per unit length. What are you talking about, John? Okay, so we know about wave speed. Okay, tension, that's kind of how tight something is, isn't it? So let's think about a guitar string. We can work out the wave speed on that guitar string and then other things like frequency, as long as we know the tension in the string and this thing in the mass per unit length. So the tension is how tight we've wound that guitar string. If you've ever played with the guitar, sort of like ding, 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 ding. As you tighten it, so the pitch goes up, doesn't it? As you increase that tension. Okay, you can do your own impressions yourself. Okay, so the thing that may be a little bit new is this mass per unit length. Well, we know what mass is, yeah, kilograms, all that kind of thing, yeah, kilograms. Per unit just means we're dividing by it, and then the length. So what we're saying there, this is a quantity for the guitar string. If you look closely at guitar strings, you'll see that they're different thicknesses. if you've played a guitar before. So there's 6 strings, but I haven't got 6 fingers, so we're going to have to just pretend. All right, but the bottom E, we call it, the bottom string, is quite thick. It's actually wire, and then there's another wire wound around it. We do that to help get the note of the string without the string being too long. Has anyone played a sitar? I think they call it a sitar. Sitar? Any? I think very popular in India. Okay, these are guitars, but they've got massively long necks, and they've got massively long necks because they maybe at the time they designed them, they didn't have the technology to increase the mass per unit length by winding another bit of wire around them. Okay, so it will be interesting to see. I'm not actually looked at it, but that must be the reason why sitars are a different length of guitar rather than a normal guitar. Okay, so we give it the symbol mu, Greek letter. Oh, is Paris still here? How do you pronounce that? Is he here? So I pronounce it mu, but you might pronounce it me. I don't know. Me, mu. Which one? Doesn't really matter. I'm just interested. Okay, so Greek letter. The second one, me. Okay, yeah. So science, we incorrectly call it mu, but it's actually me. All right, and it's a U with a long bit at the front. Okay, so what do these terms kind of mean? And let's relate to the equation. So mu is the mass per unit length. Me, yeah. So me is the mass per unit length. So all we do is you're given the mass in kilograms divided by the length of the string. Mass of the string divided by the length of the string. That'll give you the mass per unit length. Not too hard. Now you're not given that in the formula, and it makes me wonder. Are they going to, they might ask you, they might expect you to remember that. Or they might give you that formula. Or they may just give you that quantity. I don't know. We don't know what's on the test, do we? But that's the idea. It's just, so you just need to remember that's mass per unit length. That's what that is. And it's just the mass of the string divided by the length. I'm going to give you some practice questions using these. And that's what I want you to do. Just divide one by the other. Okay. To give you the mass per unit length, mu. That'll go into this formula. You are given this formula, okay? Looks a bit interesting, doesn't it? But it's not that bad. We've only got 3 variables. It's only because they've thrown in a square root that it makes it look a bit more interesting. Wave speed is the tension in the string divided by the mass per unit length of the string, and then we square root the lot. Okay, so we might look at a quick example of using that, but they do want you to be able to rearrange that formula, so I'm going to show you how to rearrange it as well. Okay. All right, in your formula sheet, let's go. Sorry about this, got to crack on. And you know what I might do to make, because we're a little bit behind where the other class are. So what I might do is I might pause, and then I'm going to carry on going through the other sheets that I'll upload, and but I'll record it so that you can then watch it afterwards, just so that we've covered the same amount of stuff. All right, so you'll have to watch out for it. It takes a little bit for it to okay, it takes a little bit for it to sort itself out when we do these videos, and then but it should be there by tomorrow. All right, so here's an example. Maybe I'm just going to keep that up there too. So imagine you're told the mass of a guitar string was 5.4 times 10 to the 3 minus 3 rather. Keep an eye on that. Length is 0.6. First thing I need to do is work out the mass per unit length. Okay, mass per unit length is the mass divided by the length. I'll take the mass, divide it by that into a calculator, shove them in. You can all use a calculator. I come up with that number. Mass per unit length, so it's kilograms per meter, not per meter squared, just kilograms per meter. All right, so that's the mass per unit length of that particular guitar string. Okay, I think I got the data on this, so it's like a bottom E. Okay, what do we do next? Okay, well, if I want to use that formula, now I've got the mass per unit length. If I want to work out the wave speed, I've got to get involved with the tension. So they'll need to give you the tension if they're going to do this. So here's the tension. You can measure the tension. If they give you that tension, you've worked out that, you need to work out the velocity. How do I do that? All right, I'm going to look at the equation. The tension is 8.83. Ta-da! The mass per unit length is 9.03 times 10 to the minus 3. I've worked that out before. Ta-da! Divide one by the other, square root it. So if you've got a Casio calculator, you might want to hit the square root key, hit the fraction key, shove in your numbers, hit the equals key, and you should get 98.9 meters per second. So have a go with this at home after, just to see if you get the same thing. Okay, and that's the wave speed. That's your velocity. I'll just sneak that in there. the velocity. Okay, and that's great, job done. All right, they may take it further, and so now you've got the wave speed. Then what if they were looking at a particular guitar string like that? I appreciate this is quite quick, so have a listen and watch the videos again, look at the notes. What if they said, what's the frequency then of the guitar string that's weighted as we just talked about under the same tension? All right, so let's have a look. So they'll need to tell you maybe the length of the string, okay? So so from the length, if it's just that, we know it's the fundamental frequency, we know that length corresponds to half a wavelength. So to get the length of the string, to get the wavelength, if the length of the string is 0.6 of a meter, then we just double it. So 2 times the length will be 2 times 0.6, which is 1.2 meters, first thing. Now I've got the wavelength and I've got the velocity from the previous question. That was the previous question. We're just going to use this. Velocity is frequency times wavelength. I need to rearrange for the frequency. Use my triangle, but it's just velocity over lambda. Put the numbers in. 98.9 meters per second divided by, where's the length? There it is, 1.2 meters, and we work that out, and it comes out as a frequency of 82.4 hertz. And that'll be the pitch or the frequency of that string will vibrate at. All right, and that's kind of what you do. I'm going to give you practice questions to follow that, so you might need to go over that again a few times and then try practice ones. So it is past, so I'm just going to do this last little bit, if you're right to stay for a minute, and then I might do a separate video on the optics bit so far. So Ashan, watch the videos, look at the notes. I know I'm going to do this very quick, and then when you watch a video, pause it, take in what I'm saying. Use it. The videos are not designed. When we do videos, you can control the speed and how quickly people go through things. So yeah, it will make sense when you go over it, and if it doesn't, then we can have a quick look again after Christmas. Okay, so I'm just going through this a little bit quick because I want to finish this bit, and I'm not seeing you next week, but there will be work on Classroom, so keep an eye out for that. Make sure you're doing the work on Classroom. If we have v equals t over mu, how do we rearrange that to work out t? What are we going to do? So first thing is I might swap that round. So put that on that side and v on the other side. That's what I've done there. Let's take it one step at a time. Okay, that's great. I've got the unknown thing on the left-hand side. What am I going to do next? I've got a square root. I want to get rid of that square root. What am I going to do? I'm going to square both sides. Opposite of square root is square. What happens then? It disappears on this side, but I've got to square this side, so that becomes v squared. Okay, last thing, and I could use a triangle if I really wanted to, but to get t on its own, I need to multiply both sides by this mass per unit length symbol. It will cancel on this side, but if I multiply on this side, I've got to multiply on that side, and so it comes up. Okay, and so you get that. Right, very quick, but go through this again. Break it down, practice rearranging the question. Okay, it comes out to be that. Not too complicated, but there's a couple of steps involved before you put your numbers in to work out the tension, if you did. All right, and then the last one, maybe before people disappear. Oh, great. Okay, come on. There you go. Lovely, that's the formula in the formula sheet. What if you had to make the mass per unit length the subject? Yeah, what do we do? First thing, I'd like to swap it over, get the mass per unit length on the left-hand side. I'm going to do the same thing again. I've got a square root. To get rid of the square root, we do the opposite thing. We square both sides. It disappears here, but we have to square the v. And again, this time, maybe it's a little bit tricky. I'm going to put it into a triangle if you want to. So t over mu, so t would go on the top, would go on the bottom. And then if we want to work out me, I'm going to put my finger over that. I'm left with t divided by v squared. It becomes t divided by v squared. Put my number for the tension in, put my number in for the velocity, but square it, divide it, of course, and then equals, and that will give you that. Okay, so they want you to be able to rearrange that equation. I appreciate that's very quick. It will take a few of us a couple of goes to get our head around that, and then practice it. Like we said before, have a look at it, try and remember it, cover it up, have a go yourself, compare your answer with the original. If you're getting it, brilliant. If you're not getting it, then have another go. Cover it all up, have another go, that kind of thing. All right. Okay, so that was very quick at the end. We are over, so we are going to go in a bit, but I'm going to just do a little bit of recording, and I'll try and put that on there for the optics bit too. Okay, and I'm going to put some other videos on optics and things like that that will help you too. Ties in with some of the practical work we did last week. All right, just want to encourage you, revise. All right, over Christmas, make sure you're having breaks, a break. But you could revising for at least a week. I think a week is a good amount. Yeah, there are lots of resources on this kind of thing. So if you've got a resource and it's a go-to thing, then have a look at those. Absolutely, you said thanks. But what I might suggest is even if you understand something, do make sure you're revising it, because even when we understand it, we do forget things over time. And so even though you understand it, by regularly visiting it, it's going to make it a lot easier you forget more slowly. So do that. All right. Sorry, it's a bit rushed at the end. Okay, but I say when we want to put the videos up, have a look at those again. Have a look at the handouts. I'll make them available. So the notes from today, and keep an eye out for work that's going to come up this week so that you can complete next Thursday. And also, I'm going to put on there as well a few other things that you can go through over Christmas, so that our last lesson together, we can whiz through any last little bits we've not done together. All right. Okay, so have a look out for those too, and good luck with the revision. Best of luck with it all. All right. Okay, so thanks very much, and I'll see you in a bit. Okay. Stop recording first.